Hello and welcome back for another presentation on weather and climate. This time we're going to introduce mid-latitude cyclones. Now within this presentation we'll obviously define what are mid-latitude cyclones. We'll also compare the differences between them and hurricanes. We'll also discuss really the foundations of these cyclones, where their origin is, what energies are required in order for them to develop, the direction in which they move, and then also just looking at the fundamental cycle from beginning to end of a cyclone. I hope that you've enjoyed the video so far, and I'm excited to share yet another one with you here, and let's get going. So to begin, let's start listing some of the similarities and differences between mid-latitude cyclones and hurricanes. So the first thing is that mid-latitude cyclones, as the name implies, develop and form and thrive in middle and higher latitudes. They are large storms within those regions. It's also not uncommon for them to originate and to travel great distances on the surface. Now hurricanes, on the other hand, although very similar, large storms, but these in specific develop within the tropics. Wind speeds are much greater. It's not uncommon, for 74 miles an hour. So we do find that the wind velocities of hurricanes are much more intense than that of mid-latitude cyclones. Another thing that we see as a big difference is that mid-latitude cyclones are very large, 1,500 to 5,000 kilometers in some instances, depending on the energy source and things like that. Hurricanes are significantly smaller in diameter, but again, don't let that fool you. Even though hurricanes are smaller, they're much more destructive and aggressive because their wind speeds can also be a lot higher than that of mid-latitude cyclones. So a couple other things I wanted to point out as similarities and differences. Similarities: they both have low pressures in the center. Similarities: they can last several days. Similarities: they spin counterclockwise in the Northern Hemisphere. So they still operate very similar, but going back to some of the differences, hurricanes are barometric in formation, so there's no fronts. Hurricanes have an eye and sinking motion at the center of the circulation, and also the big one is its fuel. Hurricanes in particular gain their energy, or what fuels them is latent or stored heat that has been released, while mid-latitude cyclones, their fuel is thermal gradients. Other things that we'll talk about in a moment that are big differences is, again, the length of day and also, the direction. So as an example, we find that mid-latitude cyclones traditionally move eastward, while hurricanes move westward. So we do find that there are some, similarities in functionality, but significant differences in the way that they operate and their development. So to kind of put more of this into perspective, I wanted to share this next slide here. This is showing a map projection of the world, and we've got this nice little goldish equal sign. The equal sign, the gold bars, represent the zone in which the mid-latitude cyclones will develop. So we find that this is the origins, and then right in the middle is the equatorial zones within subtropics. Equatorial subtropics, that's going to be where your hurricanes are. So they're two very different areas that we can see both laterally, we can also see spatially. Now moving into this next slide, I thought this would be really efficient and effective and helpful. This is a very short video showing the development of a mid-latitude cyclone in the United States, in North America, moving its way into and towards Canada. So I'm going to hit play so we can watch it. So it's developing in the lower left area. We can see that the air is moving counterclockwise. We can see that this is kind of the center of that development. Look how large this area is that's being curled into, creating that nice circular motion of that mid-latitude cyclone. Now it's crossed the border there into Canada. Again, massive. Look at how large this is. So this is a great representation, a visual representation of a mid-latitude cyclone. Things to note: it moved from the west towards the east, so it moved eastwards. But then if we look at this other map, which I think is really helpful, this is just putting two of them on the same board. Again, look at how much detail has gone within this mid-latitude cyclone, going from Texas all the way into Canada. Then we can look at the hurricane that's right down here in the middle. So again, functionality still same. Low pressure systems are in the middle, so on and so forth. But the big thing that we notice is one, the area in which it's found. So we see that the mid-latitude cyclone is again within the mid-latitudes, and we also can see here that the hurricane is found within the Gulf, where it's gaining its fuel mostly, right, from that latent heat that is being, forced up through evaporation. So this is a great diagram. This is a weather map showing both a mid-latitude cyclone as well as a hurricane at the same time. So we get to kind of see some of those elements. Now, a couple other elements, as we were saying, of mid-latitudes and hurricanes is some more information about the mid-latitude cyclones. So again, they normally exist for between 3 and 10 days, moving from the west towards the east in overall direction. Precipitation types will vary between rain, freeze, rain, hail, and even snow. It just kind of depends. Generally not incredibly extreme, but then again, it can happen, right? Depends on how long and how these systems are much larger, so they can last again a lot longer, 3 to 10 days versus a quicker storm that travels. And then latitudinal cyclones cause much less destruction and damage compared to tropical cyclones. And again, that's just due to their vorticity, their speed, the fuel, the energy in which is causing these to develop and to move. Now, going back to another map, I just thought this was really nice. So this map here is a globe of the world, and it's showing some of the really important zones. So we can see that what's been identified is the polar jet stream. We can see that the subtropical jet stream and also the ITCZ, or the intertropical convergence zone. So we can tell within this area here, within this kind of like a peachy pink color, this is going to be our equatorial zone here, as well as our tropical zones, in which we find that hurricanes will start getting their energy and form. We also find that within this green area in particular, that's going to be our subtropical jet stream, between that and the polar jet stream, which is our subtropical zones, which is going to be essentially where we're going to find our mid-latitude cyclones. Now, things to note is that most of our hurricanes will originate farther south than the jet stream itself, but then they continue to travel westward as they gain their energy. So again, other things that we can push out within this model, the green areas represent our subtropical high and desert areas. We can see that, and as we know, looking at weather and climate, that there are distinct patterns, whether it be laterally, whether it be continentality, the location in which that landmass is in relationship to water. Is it a peninsula almost completely surrounded in water? Is it more inland? Things like that. So we start to see that there are very distinct patterns. But I think the main walkaway that we have so far are looking at, because we're going to talk about hurricanes in another presentation, that they're very similar, but to really distinctly know the differences, the origin, the source of energy, the direction in which they travel. So very distinct things that make them different, mid-latitude cyclones, compared to hurricanes. So the next part that we'll talk about is the actual development of a mid-latitude cyclone. So let's discuss the development of a mid-latitude cyclone, or MLC, going forward. I have certainly talked about this in other presentations, specifically when it comes down to the presentation that discussed fronts, where we had warm fronts, cold fronts, occluded fronts, and stationary fronts, and how the example I gave in that presentation is how do they work with one another and how they continue to change, and they can cause motion and things like that. So the purpose of this is really to talk about specifically the mid-latitude cyclone, the steps that are needed within these 5 steps from beginning to end of that development, and also to observe the different types of fronts that are within that development, and to talk about kind of those steps. So let's begin with that first step. The first step is that the polar front separates the cold easterlies and westerlies in this diagram. So we can see that we've, the name that we give the winds is, denotes the direction in which the air was coming from. So an easterly means that the wind is coming from the east and traveling west. So we can see we've got a cold front moving in one direction, while the separation going in one direction and warm front going the other. So we can see that we have the meeting of a cold and warm front in this diagram. We also can see slightly, kind of from a bird's eye or oblique view, that the cold front is still underneath, or underneath the warm front in particular. So then we move into the second step. So what ends up happening is a kink will form on the front, and the cold air starts to move southward. The warm air is then able to move northward. So we call this cyclogenesis, which is essentially the extratropical cyclone development. We see that, you're beginning that counterclockwise dance, that slight rotation because of that kink, or this little bubble that kind of develops within that line. So we're starting to see the beginning of a rotation. So then we move on to the third step. Now, the cold air continues to move southward, and the warm air will continue to move north. The fronts will develop, and the low pressure will begin to develop in the middle. So now we're starting to see that the low pressure system and the warm pressure system have now been completely separated, and they are starting to chase one another, and now we're starting to even get to the point that a low pressure system is developing in the middle. Things that we can also see is that because of the cold air converging within that warm, we're starting to see two different forms of precipitation are occurring. The one here on the right-hand side is because that warm air is being forced above the cold front, so the air is cooling down and condensation can occur. And then we can also see here, because the cool and stable environment is meeting that warmer air at that boundary zone. So now we're starting to see again, that it's no longer a dance, now it's a big rotation, which leads us into the fourth step. Now, the cyclone will mature, the warm and cold fronts become well more established, and we're now seeing essentially weather. We're now going to be able to identify the different types of weather, but notice how large this system has become between both the cold and the warm fronts, and in their meeting zone. It's now taken up almost the entire diagram. So they've, and its maturity have become very, very large. Think back to that animation that I showed you, how you could see it was a very small zone, and then as it began to really, rotate it, counterclockwise, how big it began getting in its final stages of maturity, which take us to the last step, which is really when the cyclone occludes and it's the end of its cycle, and it will begin to decay and weaken. So that's, in a sense, where it kind of goes back where it started from, where the cold and warm fronts are now going to be stacked on one another, and it becomes almost to a standstill. But it's kind of the dissipation of that system. So those are those 5 steps. So I'm going to kind of go back to this other slide here so we can see, within the cycle, but we're starting to see essentially that rotation piece. It's flat as it begins to spin because of that kink. The cold front's able to move south, the warm front's moving north, and then they continue to then create weather, and we start to see that within the cloud formations, and we can, observably from space see that it's moving counterclockwise until it becomes an occluded front, and where it actually concludes its life cycle. So the next slide that I wanted to share here is just showing those precipitation patterns. So this is essentially looking back at our stages, going back to this diagram here. We can see that it's within the 3rd and 4th stage, and we can see that we have uplift by convergence, uplift by overrunning. That's again where we started to see precipitation here, precipitation being forced here. We also have our low pressure system here, and these percentages are giving percentage of rain. What are the chances of rain? 95%, 90%, and then as it gets farther away, it becomes less. So this is looking at it as a storm system, and the diagram on the right is showing it as a weather map, looking at the isobars of the pressure, the barometric pressure, so we can start to see both of those together in that pattern. So the next thing that I would like to speak of very briefly is vorticity, and just looking at the rotation, which I think helps when looking especially at this diagram, how we have this cold air, converging, coming down into a low pressure. This warm air is forcing and pushing things northward. So we're starting to, we see in this diagram the motions that are being pushed forth. But let's talk about the actual vorticity, or the rotation of some of these areas next. So to wrap up this presentation, we're going to talk about vorticity. We're also going to talk about divergence, convergence when it comes to both these, mid-latitude cyclones, but also looking at both lower and upper air models when it kind of pertains to all of these elements combined. So what is vorticity? Well, vorticity is the turning of an object, usually with respect to the vertical direction. So we classify vorticity as one of two things: clockwise as a negative action, or counterclockwise as a positive action. Now, that being said, relative vorticity means a vorticity that is relative to the Earth's surface, which can take, that can be part of, perhaps speed and or the curvature of the Earth itself, and those will certainly play a role on the vorticity observed. And then lastly, another vorticity is the Earth vorticity, which is the planetary object motion due to the Earth's daily rotation about its axis, otherwise known as the Coriolis effect. So all of these work together. It's all vorticity at the end of the day, but they work and operate in different functions throughout the course of our planet, and especially when it comes to just its interactions with massive and large extreme weather and storms. So what I wanted to, again, we've seen this before: low pressure system, high pressure system. We're looking at a counterclockwise motion with a low pressure system. High pressure, we're looking here at a clockwise rotation relative to the Earth's surface. We also know that we have the actual rotation of the Earth, which is a driving, element, fuel, as it were, when looking specifically at the rotation in the northern and southern hemisphere and how those will change directions. So, a low pressure system will move a different direction in the southern hemisphere, and so on and so forth with high pressure. So, what we're able to look at within this, in addition to, is the upper air motion. So, an upper air motion, this is actually looking down. This image is looking down at these different systems. So this is upper air moving, and as you can see, when it hits to this location here in the trough of an axis versus the ridge of an axis, so this system here is a counterclockwise rotation. Oops, as I move it, a counterclockwise rotation here, and this will be a clockwise rotation. So what's interesting about that is we're seeing within this counterclockwise is it's moving items. It moves the air, the upper air motion in that direction, and the clockwise will move it towards the right. So we're able to see this change. And again, this image is looking at that upper air motion, again, looking down on the Earth's surface from above, and we're looking at really, how is vorticity, whether it be clockwise or counterclockwise, is greater than just surface air. That it's it kind of moves everything together. So then let's look at this convergence and divergence. So this is looking again at the surface. These are looking at a couple things. We're seeing the barometric pressure in these isobars, so these pressure gradients, and we're seeing that whether the distance is starting to increase or decrease. So if it's starting to essentially spread apart, it's considered divergence aloft, which is caused by decreasing vorticity, which draws air upwards naturally and providing a lifting mechanism that can initiate or help maintain that surface low pressure. Now, on the other hand, when we can see that the area is being pushed together, that's convergence aloft, caused by the increasing vorticity. So it's spinning and it's forcing in tighter, promoting rising air and surface high pressures. So I think the best way to really see both both of these families together, the upper air motion and the divergence and convergence, is linking it. How does it look together? So here we have upper level divergence and upper level convergence. So we're looking at the vorticity, the speed, the rotation and the direction, whether it be clockwise and counterclockwise. So we're looking at a storm system or a cyclone or anticyclone here on the surface. We can see that what's happening within the high pressure pushing down, low pressure pushing up, and how that affects upper air motion as well. We have that ridge and the trough that are found within here, and because of this motion, as you can see, it's forcing the air downward and then back upward again. So we kind of get that nice, again, ridge and trough, crest and trough motion and upper air mobility. And so we really get to see all of these things together. The main purpose of talking about these last things, vorticity, upper air motion, and then also looking at convergence and divergence, is just to paint that bigger picture of, okay, so we're looking at cyclones, mid-latitude cyclones to be specific. We're looking at their, their origin, the source of their energy, how they operate, what they work, things like that. We looked at a couple videos, looking from above and seeing the cloud coverage. Well, this is really showing, when we're observing that type of cloud coverage in motion, these are the other elements that are involved. So it's not just what's happening on the surface. There's also upper levels, above the surface that are being, that cause an effect of these cyclonic motions based on pressure. So again, this was Crash Course. Again, 5 models, 5 steps into the development from the beginning to when it becomes occluded. We saw a couple different elements when it comes to looking at vorticity and rotation and things like that. So I hope this is helpful to kind of paint the picture of the greater mid-latitude cyclone. Again, the next one, which would be very helpful within this, we'll be looking at the differences and moving forward into hurricane development. So I hope this is helpful. Don't forget to like the video below. Don't forget to subscribe if you haven't. If you have any questions, be sure to comment, and we will talk soon.